I was telling George, I always like talking to this group because I always get more from it, I think, than the folks I talk to, because I get good comments and good questions. And a level of enthusiasm I just love, because I love systems so much, and I think it's such an important thing for young people and universities to understand and begin to kind of, you know, teach and to incorporate into programs like SISE. So I always love getting the feedback for it because it's something I love. I'm going to talk about systems level approaches to sustainability and energy, but I want you to note that I am a director of a systems science center that's within the Global Security Sciences division. So I'm going to show you how a security bent really is very similar in our minds to the sustainability and energy security issues that we face. So in saying that, this is how we see, you know, sustainability and security. They're really related topics because, you know, all nations require these basic things of food, water, energy, and critical materials. And those threats to those natural resources, not only here in the United States, but what happens in our neighboring countries or overseas, comes back and impacts us in a lot of surprising ways. And that's what systems is all about. And so we really want to look at this global resource security as a complex challenge, and really you look at the kinds of things as we want to identify the global resource threats, where are the vulnerabilities for water and food and materials, look at the risks and plan for prevention, and then of course we want to be able to do this not in the sense that we want to react to it, not to plan to like how we're going to react to it, but how can we build resiliency now? So we can mitigate, you know, we can't mitigate everything, the surprises and the black swans, but you can think ahead enough that you can build some resiliency in your systems. And that means not only in your environmental systems, but in your manufacturing systems, your economic systems. And so that's kind of what systems is really intended to help do. So let's talk about energy security first. And so, of course, this is a definition. It's the core ability for security and economic prosperity to supply affordable, reliable, sufficient, and sustainable energy. And that's a big task. And who's responsible for energy security? Like in the country, in our country, who's responsible for energy security? Nobody owns that problem, right? The problem's owned by many different stakeholders, and that's another characteristic of systems that we have to grapple with. So this is what we look at it from a security perspective. Like Africa has more than 85% of the rural areas lack electricity, and they're supposed to double their population between now and 2050. So energy is a huge problem. India, power outages. They have really unreliable electricity, and they're looking desperately because they're, of course, if they don't do anything about the coal that they're using. I mean, I had someone tell me that no matter what all the other countries do, if India does not do anything about their usage of coal, given their population growth, that all the other things that we're doing won't matter. So they have to try to figure out how to do it, but keep it reliable and make sure, so what, is it going to be nuclear? Will it be renewables? Will it be all of the above? But what happens in India really, really has an impact back here to us, and so we have to recognize that. Brazil, US, Canada, so even in developed countries, and as George mentioned, you know, even in our country, the vulnerability of our infrastructure and of our energy infrastructure is really, put it this way, I've been into meetings in DC and some of the areas that are classified, and it's pretty darn scary just how easy somebody could really do some damage to our electric utilities and then other infrastructures too. So that's why energy security is really important. It's sustainability of energy, but it's also the reliability and the economics of it. So it's also, you know, getting us independent. So we always think of energy security, I think a lot of the United States, a lot of folks, especially my parents' age for some reason, it's all about independence. We don't want to be beholden to any other country, and we want to be able to produce every drop of oil, every, you know, gas molecule. We want everything to be in our country, and we can shut ourselves off, and we won't have to worry about it. But then again, we really want the pipeline, because we really would love to be able to take natural gas and produce liquid natural gas and export it, because we could make more money. But natural gas is really important to manufacturing right now because our natural gas prices are very low. But when we start exporting it, now it's a global market, we don't control those prices as much. It's like oil, right? No matter how much we produce, oil prices still go up and down all over the place by actors overseas. So this is a system, right? The second, third order effects of something you might think as simple as putting a pipeline in, even aside from the environmental impacts of that, but look at the economic impacts of it and look at the security impacts of it. So there's a lot more things to it. Okay, so this is energy security is more than just energy independence, because if you look at the kinds of things that go on in the world, a lot of things, we know, for instance, and we always say that people fight over oil, right? They'll fight over other kinds of energy too. Energy is going to be, and will continue to be, no matter how hard we try, a geopolitical issue, because there's population growth at the same rate as we're trying to get energy resources. So it's not only that we get energy resources up to do the population we have now, but the population keeps growing. And in addition to that, the population is moving, and we'll talk about that in a minute. So environmental security, as we look at environmental security as protection of natural resources and the ability for people to utilize their natural resources, share and export, have trade of natural resources, but something that we can look at as far as fair trade and that kind of thing. There are a lot of things that could happen between now and, let's say, even 10 to 15 years from now that can be really interesting. Imagine if we do have major droughts. So water will be something that people really have contentions over, right? Right now there's a lot of collaboration about water in some of these desert kinds of places in the Middle East and in Africa. But if you put enough pressure on those different places and you have enough drought, you could see that if one country is doing something that is viewed by another country as to be hoarding water or not letting water flow through watersheds, there is going to be some contentious issues that will come up over water. Food. So if food becomes a secondary impact of the droughts and water, food could now be something that could be almost an illicit material or a commodity, because you could see people black marketing certain kinds of foods. And so there's all sorts of things in the future, and I'm not meaning to scare everybody, but you know, it's more than just the environmental impacts. It has a lot of impacts on security. So when we look at energy, we do feel really comfortable, and this one would have been animated so you could read every one of them, but it's really becoming more evident. You know, it's hard to tell because we go back and forth on whether we believe that man is inducing change in the climate or not, but I'm gauging by the fact that I have very, very conservative relatives who are starting to say, you know, we kind of think maybe there's something to this. I gauge that as a shift in the right direction. So it's slowly evolving, and I think it goes as fits and starts, right? But how might climate change impact? And another animation would be there's not enough water, or there's too much water. And behind there is food, energy security, damaged infrastructures, and then, of course, shifting patterns of diseases. When we see things like warming of the southern parts of the United States, we now have dengue fever, and we're starting to see kind of shifts in some of these kinds of diseases that weren't there before, especially insect-borne diseases, and we can imagine waterborne diseases too. So what about population growth and urbanization? So we're talking about smart cities. One of the things that we're working on is a workshop on what we call mega cities. Because the smart cities is going to be great for folks that are in developed worlds, that we can really be smarter about our cities. But the biggest cities and the most scary cities are the ones that we're going to grow into third world countries. Their rapid rate of population growth, coupled with resource contention and resource scarcity, is going to force lots of people into very big mega cities that won't be planned. They won't have infrastructures that will be able to serve that population. Food and water will be an issue, and disparity of economic prosperity. You know, these are realities that I think whatever we can do as a country to understand systems, like if we use our smart cities to understand flows and stuff, we should be sharing that, and we should be exporting that knowledge, because it's going to be really needed in a lot of places in the world. So this is where I start saying we need to start thinking systems. And I love this cartoon because this is, you know, we really in this country tend to just really kind of focus on just what's happening in your neck of the woods. And then, you know, not even looking at the fact second, third order effects that just next door might be something very terrible. So system thinking is really, and this is why I kind of made a point of saying that systems science is different than systems engineering. Systems engineering is actually kind of a type of system science, but it tends to be very much focused on reductionist types of thinking. So you reduce it down into its parts, and then you put it together. So it's based on physics, and it's based on things that you can kind of like really study the components of, and then once you really know what the components are doing, then you can build it back up into how it works as a system. And so that's really great, and that's again how manufacturing works, and that's how, even in a sense, city infrastructures work. But systems is much more, and again, when I talk systems, I want to really emphasize this because I do for everybody, is when you're talking about system science and you're trying to simulate something, we're talking a lot about putting people into the simulations. So I always say that we're not predicting. What we're hoping is to provide foresight and anticipation, to give people the ability to say, here's a set of plausible kinds of futures based on what we know, but we can't tell you it's going to be this one because there's too many variables when you're talking about systems. And we're not really interested in controlling the system because these are big systems, and we'll talk about wicked problems in a minute. You can't control them, but what you can hope to do is influence them if you understand and have enough foresight, if you can model them to the point where you say, well, you know, if I modeled a suite of scenarios and it seems like that there's a cluster of 3 plausible futures, well, maybe you look for, now that you have that, signals and clues as to which one of those it might be going down. So I've seen this before because we simulated it. I didn't know it was going to go this way, but now that it seems to be going that way, we simulated it. We can anticipate what might come next and what the second, third order effects. And that's really different from people who come from modeling backgrounds who are really talking about, you know, physical models. And I used to do physical modeling. I used to do hydrologic modeling. I used to do soils modeling. And it's hard, but it's not complex. That's the difference. It's complicated, but it's not complex because I can break it down. I understand the physics. It lends itself to laws of physics. But the systems we're talking about don't necessarily lend themselves to laws of physics.
So is there a definition for complex systems? And what's...
Thank you. I planted you just for that reason, didn't I? A couple more slides. So the interdisciplinary teams is so crucial, as you can imagine, right? So this kind of program, this SISE program, is just so cool. Because you guys are really mixing up a lot of disciplines, and people have to work on teams and really think about, like, well, what is, you know, I think it's this way. Well, that might be true, but look at it from this perspective. Or if we did this, well, yeah, that would solve your problem, but it makes a big problem for me over here. So you start kind of seeing that this is the kind of thing that people, if we really want to really kind of solve, and I don't want to say solve, but if we really want to manage and kind of the dilemmas of the world, you have to work as a team. So this is the System Science Center, which is a center that we just started at Argonne just in September. And I am directing it. I have worked in systems for many years. I have put together integrated modeling systems for environment, energy, national security, infrastructures, but I don't have a PhD. Because the reason I don't have a PhD is because I could never narrow myself down. I am just not that kind of person. I'm always looking at, how does it integrate with this? And if I would have done a PhD, I have a master's in soils, I would have had to probably narrow it down to some really narrow part of what soils is. And I'm like, oh, wow, shoot me in the head. That would be, I mean, I want to do watersheds next. So I haven't, but I am going back now because the system sciences are becoming more and more something people are recognizing. There still aren't a whole lot of programs in the United States, hence the reason for going to the UK. But I'm hoping, and I see some real promise, and some of the universities are starting to teach a curriculum of system science, which is encouraging. So this is our definition of a system. So it's a set of connected elements forming a complex whole. So system science is an interdisciplinary field, obviously, but it really looks at the interactions and interdependencies, almost before it looks at the elements of the system. So when I look at things, I might kind of, in my mind, I know, okay, it's manufacturing, and I know that there's smart cities, and I might think of these different things, but I immediately look to where I see the web. I see the interconnections. I want to understand those interconnections. I want to know that if I affect something here, are we sure that that's a good answer? Because look, if I pulled that out of my system, and I didn't bring my toy that I always use, I should have brought it, but I have a toy that illustrates this. If you pull up one thing, here are all the things that trail with it. If you map it all out, you're very cognizant then of knowing that you can't just affect an element without knowing that it has tendrils. And maybe that's okay. Maybe the tendrils will come along with it and it'll be all positive, but maybe, you know, you push it this way and this element becomes a really big problem. And I don't know if you want to sit for a while maybe over drinks and we can talk about the many things in this country that we've done in complexity that we thought we were doing very, very, very much the right reason, but huge negative impacts happened everywhere. And it's because we tend to really think down our stovepipes and really narrowly. And so this is something that I'm hoping that we could educate folks on, including our government. So we'll talk about that at the end of the talk. So what we provide is this understanding of physical, socioeconomics, and anticipating. So we have an actual anticipation foresight science that we're working in too, which is again something Europeans have a really big, I mean, UNESCO, World Bank, they have whole foresight teams. And in this country we're like, foresight? What is that, a crystal ball? No, it's a discipline in a science. Anticipatory systems is a science. We don't tend to recognize it much here, but. So what are complex adaptive systems? So complex adaptive systems is a specific kind of system that we model at Argonne. We have a lot of experience in this. And this is kind of like the bottom-up approach. So if I were to say that I don't know in a complex world how it really all interacts, because you know it's hard to see that at the high level. If you can come down and see it, it looks like spaghetti. But if I can understand what are the basic kinds of behaviors of each of the elements of that system, and I can model those and the way that they interact with each other, more importantly, not just what they are, their characteristics, whatever, but how they interact and trigger off of behaviors of other things. Could I model just the simple behaviors and see what emerges as the complex system? And so that's what this kind of modeling is really good at doing. And we've used it for doing electric power grid modeling, biological systems, social groups, and so it has a lot of applications in a lot of different fields. So what is an agent? So again, the agent is autonomous. It's not like a system dynamics model or another model where you've actually done all the experiments. Let's say it's a physical model, and you tell the model this is how you should behave, and it has some sort of like, you know, director, and the model directs, here's how it all works. Here they're autonomous. They get to be able to react to, change their behaviors kind of on their own. They have learning, they have ability to say, well, if I did this over and over again and I didn't get my goal, I could do something else. They interact, obviously, that's one of the big points, and then they have attributes, and then they have behaviors. And then you can change the behaviors. You could have a population that has certain behaviors and another population that has different behaviors and see how they interact. Or you can have learning so that they have one behavior when they start, but then because of things like resource scarcity or whatever, they change their behavior. And so this is the style of modeling that this kinds of advanced agent-based modeling does. We have a system at Argonne that is free open source. It's the largest agent-based modeling system that there is in the world, open source. And we have it ported to high-performance computing. It has something called Symphony around it that gives you all these open source tools like statistics packages and data mining packages and visualization packages. So when you're doing your modeling, you can export things out and you know, analyze them more. And these are just some examples of some things we've done. So the first one up in the left-hand corner is one we're just working on. It's in the Arizona study area. We're simulating the urban power water supply with different management agents, different consumer agents, and different agents that basically are government regulatory policy agents. And so we're looking at various different scenarios and various schema to see what that impact would be on water. This one was an NSF grant. We work with some folks at the University of Miami that we're doing some work on agent-based modeling of potential impacts of climate change on the structure of farming in Argentina. Anticipating the spread of MRSA in Chicago, that's a project that we did. Go ahead.
How do you model human beings in the economic theory, or you guys use behavioral
Right. So human beings are modeled in a number of different ways. In some ways, one thing we can do is we can do interviews. We can talk to people about various things, and we can use the interviews to kind of come up with proxy behaviors for probably more like a group of people than it would be just one individual. In the MRSA project, what we did is we actually took the census data and created a synthetic population that we knew there were certain ages. We knew that they had certain people worked in the suburbs and stayed in the city at night and moved to the suburbs. And so we have a way to use synthetic populations. In a lot of cases, we use social theory and social science. And so we have several social scientists and anthropologists in our staff that we really kind of bring it from the theory side. And so this is why I say it's not a model that I'm going to tell you that this is exactly the way it's going to go, because we're using theory, or we're using subject matter experts, or we're using interviews. So that's why we don't really feel like we can predict. But we feel like that we can still say, we can anticipate that this is a likely way that this might emerge given these behaviors. And then you can run another model, change those behaviors and say, and then it emerges this way, and really kind of explore. So it's almost like an electronic laboratory. It looks at what happens when you change behaviors, what happens if you introduce renewable energy, and consumers might not kind of latch onto it right away, and you can model that, okay, there's early adopters and there's people who won't be, so you can kind of use it that way. So it's more of an electronic laboratory than it is a predictive model. So any other questions before I go on? Go ahead.
You mentioned the word adaptive. So the idea that over time there's some behavioral changes, right? What about those cases? What kind of models are used there?
Usually we'll use something in the AI area, so your genetic algorithms, neural nets, or various kinds of ways to say that if we feel like if we could feel like there's a goal for the agent, so the agent is trying to meet some goal, and if their behaviors are not achieving that goal over and over again, then they can change their behavior, and then we can test different behaviors to see if they can achieve their goal. So they can have learning algorithms, which is really just artificial intelligence types of methodologies that you can build as a behavior so that they are able to learn and to change themselves. We did one here where we looked at the generation and actually modeled the electric grid market here in Illinois before we restructured, and tried to anticipate the behaviors that would happen in an unregulated electricity market. And turns out that the predictions that we had and the kinds of things we thought might happen actually did happen, some of them negative, and some of the things that could have maybe been done a little differently, but we felt like we did a pretty good job of kind of modeling the behavior that ended up happening. And then there's one over here I think is interesting, is basically this is taking the Mesopotamia, ancient Mesopotamia, and looking at, with the Oriental Institute, all of the records that they could find about the behaviors and the kind of day-to-day activities. And then we put in SWOT model and climate change models to say, can we kind of look to see if maybe it was climate changing that caused the downfall of society. So that was an Oriental Institute in Argonne, NSF. It's been over with for a couple of years, but I always put it up here because I think it's so cool. So here's an example. So this is an agent-based model. It's kind of actually a combination of agent-based modeling and something called system dynamics modeling. So system dynamics model is just the opposite of agent-based modeling. It comes from the top down and it says, okay, we're going to sit down and take each of the parts of the system and we're going to sit and explicitly talk about what are the buckets and the flows between those things, and you model it from the top down. And in this case, we did that for the market, the oil market. So what we're interested in here is let's say we have an oil market problem, and we have a project right now looking at this. When Yemen is at war and it reduces its amount of oil output, what does that mean to the market, and what will other actors do in response to that? Another one is when Saudi Arabia recently decided they're going to flood the market with oil. It didn't make a lot of sense for them to do that rationally from an economics perspective, but from a geopolitical perspective, it made a lot of sense, because what they did is they lowered the prices of gas and oil across the market, and it hurt their neighbors, like Nigeria and other places. It hurt them terribly, and it hurt Venezuela terribly. Now, they let up on it soon enough that it wasn't a huge impact. But what happened in the United States? I'm from North Dakota, so I know. The Bakken started shutting down. They started losing jobs because of what Saudi Arabia did. So this is a model to kind of look at not only how does the market work, but then it has this concept of the behavior of the actors. So it could be the country's decision making, could be companies' decision making, could be cartels, but it kind of says, well, if this agent does this, how can we expect, because it's not all economic. So most of what we would do is look at an equilibrium economics model, and we have it all figured out, but it doesn't work that way. They make decisions that aren't always economic, and so this is a way that we can kind of look at those kinds of things. The Foresight Initiative. This is a brand new project that we've had, I guess it's been about 8 months in, and this is the National Geospatial Intelligence Agency, part of our intelligence community, who said, gee, you know, maybe we should be looking at emerging threats. Maybe we should be using the firepower of the geospatial kind of capabilities they had, as well as our capabilities. And can we help our country kind of anticipate where we might see future conflicts by modeling water, climate change, oil, gas, and these kinds of things? So this is a big endeavor. It has Arizona State University, Oak Ridge, Pacific Northwest National Lab, an industrial partner called Agave, and Argonne. So we're all working together. We'll talk about a social project, to kind of come together to create this very flexible kind of foresight initiative architecture that will let the future analysts, and what's really cool about this is they actually pay Arizona State to start a whole new curriculum to teach future analysts how to do systems level, more of this kind of stuff than usually what analysts do is sit at their computer and they're just looking at imagery and they're saying, oh, something's happening here. It's going to be a completely different way it's a culture change for the intelligence agency. So we'll see if it succeeds, because I think technologically, it's going to be really hard, but that's probably going to be a lot easier than it is to get the cultures to change. There's more transparency. This is all open source, which is really hugely different for them. So it's really kind of interesting, and it's a really promising. And what we're doing is the interoperability architecture to bring the models together. Pacific Northwest has something called GCAM, which is it's called a general, it's not just climate change, but it has a bunch of other kinds of high-level equilibrium kinds of models in it. Arizona's got something called the Decision Theater, if you've ever seen it. It's really cool. You get to go into this theater and you actually have, the way that they use it is they use it to bring stakeholders in and say, okay, make a decision. And it's maybe a water decision. And it'll show the whole water system and everything about what they did. It will just pop up all these things on the screen and say, okay, here's what would happen if you did that. And so, well, let's try something else. And then they'll have teams come in. So it's really a pretty cool thing. So that's another project. Okay, resiliency analysis. This is something that the laboratory is just starting a new initiative on, crossing the whole laboratory. And what we're hoping to do is, resiliency is it's like sustainability in other words that, get overused and not defined well, and everyone thinks they're doing resiliency, and is it so different than what we're doing? And so, but we really think resiliency is really the real crux of a lot of things, because it's preemptive versus reactive. And it really is kind of a signal that we're starting to think, can we think in ways that really kind of are more stopping things from happening? Not that you would stop things from happening, but you really, really are more ready for them. You're more resilient to them. And that's a hard thing. It's hard to even define. So this is the definition that the group that at Argonne put together. It's the ability of an entity or an asset, an organization, community, region to anticipate, resist, absorb, respond, and adapt to disturbances. One of the things they really emphasize when they say this is that it doesn't mean that it has to bounce back to just what the system was before. It actually can bounce back and be better than it was before. And it doesn't have to be identical. It can have the same function and look different. And so this is some of the things is everyone kind of thinks, well, it will bounce back and look just like it was before. Well, if you look at something like Sandy, when Sandy hit, one of the reasons it had such an impact is because we just weren't ready for it. So if we're going to rebuild after it, why don't we build resiliency into it so that if the next one hits, we'll be more resilient to it. So the system can evolve. And these are just examples. We have a regional resiliency assessment program that we do for DHS. We did an interesting one for DOD where they were asking, because it really is interesting that DOD is almost always the first folks in when something happens at Haiti or when something happened in Indonesia. it's really the U.S. military that goes in first. And so they were starting to say, well, is there a way that because we spend a lot of money doing that, it's a lot of resources, is there a way we can kind of look at what is the resiliency of different regions of the world? Can we get some metrics to look at the resiliency, and what can we be doing to use USAID or other kinds of assets to beef up the resiliency so they're not so really just at the edge, right? So that any disruption really causes huge problems. And so that was an interesting project. And again, the hub idea would be that we have this ability that people could come to Argonne and we'd have a series of models and resiliency types of scenarios that people could build, and they could kind of almost use this as a resource. And so that's the idea behind the initiative. Lastly, we're going to talk about wicked problems. Oh, go ahead.
I just have one more question. Have you guys thought about venturing into financial systems? Financial global crisis, financial crisis? It seems like you feel them pretty well.
Yeah. We've written a couple papers on how it could be used in that sense, but politically, there isn't really anybody who wants to sponsor that. It's just too full of lots of politics. And again, it would be really difficult to let the population and folks in the journalists of the world to understand that it's not prediction but anticipation. They would immediately go to prediction, and they would immediately say, okay, this is what's going to happen, and that's just not. And so we're really worried when we put things out, even the scientific literature, we're very careful to make sure that it doesn't come across as that we're predicting something. We almost always will put like 3 possibilities, because even though we might think one's more likely, it's very hard to put one out there because people latch onto it and then they say this is what's going to happen. And so that's kind of a problem. And then with financial markets.
Yeah, the definition of resilience you had seems to fit right in.
It does. It does.
M8.
Yeah. So this is wicked problems. So now wicked doesn't mean that they're evil. It means more like, like a slang term like, man, that was wicked. It was just, it's difficult to an nth degree. And these are the definitions. It came from a paper back in 1973. It's a very well-known paper, and these are kind of the criteria for what are wicked problems. So energy security is a wicked problem, because I asked you earlier if anyone owns it, and you could say no one owns it. Multiple stakeholders. It will never be solved, right? We'll never solve it. All we can do is try to manage it. It's a dilemma versus, a problem to be solved. There are things that are unique at every time. The planner has no right to be wrong, right? Because this is so important and there's so many stakeholders, so no matter what you do, someone's going to be pissed at you, but, So these are the kind of class of things that, and I love this quote, is there's no quick fix for wicked policy problems, no glib formula, no 7 steps to crush social complexity or the way to tame your way to the top. Complexity is complexity, and the way we look at complexity is not to be scared of it. Because your first reaction to step back and go, whoa, we just can't possibly even think about trying to solve these problems. But we can't do that, right? You can't just put your head in the ground and expect things are just going to evolve and everything's going to be good. You have to try to manage them. You have to do something. So this is what wicked problem management is the kind of the crux of my PhD. And so what I'm trying to do is look at how can we as governments, could be local, could be regional, could be federal governments, or even international governments, how can we make ourselves be a complex system of our own to combat complex systems? We don't, right? Complex systems are adaptive, they change quickly, they're very complex. And what do we do in our government is we say, okay, energy, you are DHS and you do vulnerability assessment. Let's see, you're the DOE department that does renewables, but you can't work in nuclear. Let's see, you're nuclear, but you just work in nuclear, don't do anything else. And all of the budgets and all of the missions all come right down those stovepipes. And yet we're trying to solve energy security. And we just can't do it. But on the other hand, we can't say, okay, here's a problem, energy security. Let's rearrange our government so that we can address our energy security. So what's the next best thing? Well, there's a lot of research in system science that looks at how do you actually adjust and organize yourself to understand your environment if it's complex, or even if it's not. And so a lot of businesses do this. Shell was a really good, very much of a leader in this area. Other kinds of companies do this, but they say, we need to understand our environment, and we need to adjust ourselves constantly to meet the environment. And this is something called the viable systems model, which I'm adapting from my PhD, because what it does is that right here is basically the different agencies in a company. It would be components of a company. It would be sales, and it would be, you know, manufacturing, and it'd be the components. And then this up there at the top is actually the brain, which is the CEO. But in this case, we don't have one, right? Who do we usually have in these cases? A czar, right? The president will put a czar in almost every, I mean, we have a czar on birth control. I looked at all the czars we have in the nation. We have a czar for birth control. So we have czars for all these things that they have task forces. So now I'm the czar of energy security. So I'm going to pick you guys up and, okay, you have your own zero-sum games, right? Because you want all the money you can get for nuclear, because it's important to you. And renewables wants that. So I'm going to bring them all together, and we're going to come together, and then we're going to what? We don't manage the problem, we put a report together, right? And it goes, it's on a, nothing comes out of it as an active, here's how we're going to manage it. It comes out as a report. So can we use the viable system model to improve our anticipatory systems outlook? So in other words, can we look at what's happening in our environment right now? Can we anticipate where it's going? And it's a foresight modeling, and is kind of a scenario-based type of thing that helps you do that. And part of it is just systems. So I'm using a case study for transnational organized crime. And I have members, subject matter experts that are working with me that are from, let's see, I have a Chicago cop, I have someone from DIA here, I have somebody from DOD, somebody from DHS at the Border Patrol, I have something from the State Department, Treasury, and so each of them are on my advisors group. And I sit down with them and I ask them, tell me what your perspective of the transnational crime, organized crime, and its convergence with local urban gangs, what's that system look like? So we walk through, I give them cards, we make cards, we lay them on the table, how do they interact, and we build systems that are from their perspective. And so what I'll have is all these pieces of the system that will all have different perspectives. I've already started doing the research, I've got 3 underway right now, and they're quite different. Some of them don't agree. Now some people say that there's this thing called a super fixer that somebody coined. Well, they really believe it's this, but somebody else says, no, the super fixer doesn't operate that way, right? So now I'm starting to, that's good, because we can now come to an agreement, and maybe there's 2 different types of roles, you know? So in the process of actually making them create the system, I'm not coming to them saying, here's what your system looks like, because I don't know anything about, you know, transnational organized crime, they do. I'm just facilitating them getting the system picture. So imagine then we're going to have a model at the end where we can say this is strategic and not operational. It's not like I'm going to say that, okay, this guy in this corner, we're going to take him out and we know his name. But just in general, what if in the city of Chicago we, in a concerted way, took out stash houses at the same time that Border Patrol did some operation here, and that the State Department was ready for it because there would be a kind of an impact back here in, let's say, Central America. So can we build something that's strategic where they all agree the system kind of works this way, and we can actually do interventions that are systemic and anticipatory? So that's the, but these kinds of wicked problems exist in a lot of places. So this method, I'm hoping, even though I'm using a case study for transnational organized crime, I'm hoping it would be an example of a method that we could use in other areas to tackle wicked problems. So that's it. What does it take? It takes collaboration. It takes advanced tools. Argonne's working a lot on those advanced tools. But it takes education. We need people to come out of education programs that have some experience in systems thinking. I mean, all the way back into grade schools and junior highs. They should be introduced to having to work as teams and looking at second or third order effects, because then as they grow older, we can have them ready for teams that can really tackle these kinds of problems. So that's it.
Cool.